Projectile motions consist of two components, vertical components, y components, and horizontal components, x components. From the figure 2.9, the x component of velocity along AC at any point is always constant. Therefore, ux equals to u cosine theta, whereas the y components of velocity varies from one point to another point along AC, and uy equals to u sine theta. Table 2.2 shows the x and y components, magnitude, and the directions of velocity at point P and point Q. Point P is V1. For x component, V1x equals to ux equals to u cosine theta, whereas point Q, the V2 is V2x equals to ux equals to u cosine theta. X component always constant. For y component, at point P, V1y equals to uy minus gt1, whereas V2y equals to uy minus gt2. The magnitude of V1 equals to square root of V1x squared plus V1y squared, whereas the magnitude of V2 equals to square root V2x squared plus V2y squared. The direction of θ1 at point P will be arctangent V1y over V1x, and the θ2 at point Q will be arctangent V2y over V2x. Then come to horizontal projectile motion. Figure 2.1 shows a ball bearing rolling off the end of the table with the initial velocity u in a horizontal direction. So, the ball rolling off and having the projectile motion and come to the impact point B. Horizontal component along the path AB. Ux equals to Vx equals constant. And the displacement Sx is equals to R. For vertical components along the path AB, initial velocity Uy equals to 0. And you only have Ux, right? And the displacement Sy equals to negative h because the impact is below the initial position. Time taken for the ball to reach the floor, point B, will be using the equation Sy equals to Uyt minus half gt squared. Substitute the Sy equivalent to negative h, and the Uy is equals to 0. At last, you can get the T. For the horizontal displacement Sx, there is a condition below. Please take note. The time taken for the ball free fall to the point A is equals to the time taken for the ball to reach the point B. Since the x component of velocity along the AB is constant, thus the horizontal displacement Sx equals to R. Please take note. Involving any calculation problem about the projectile motion, the air resistance is negligible. From the formula for the translational kinetic energy KTR equals a half mv squared. By comparing both equations, V is analogous to omega, whereas m is analogous to I. From the formula for rotational kinetic energy Kr equals a half I omega squared. For a rolling body without slipping, the total kinetic energy of the body K is equals to KTR plus Kr. From the principle of conservation of energy, summation E initial equals to summation E final. E initial mgh equals to E final K. Procedures for projectile motion. First, set up the apparatus as in figure 2.2. Second, secure the curved railing with a cellophane tape. Make sure the meter rule is placed perpendicularly with a horizontal table. Position your eyes perpendicularly to the marking on the meter roll and take the reading. Use a ruler to hold the steel ball before releasing it to prevent the impulsive force that is exerted on it. Use a ruler to hold the steel ball before releasing it to prevent the impulsive force that is exerted on it. Tighten the string to the pendulum bob. Fix the string with a cellophane tape. Position your eyes perpendicular to the string with the pendulum bob and make sure the string with pendulum bob is perpendicular to the surface of the floor. Secure the position of drawing paper with a cellophane tape. Draw a straight line by using meter rule from the center of the pendulum bob. Place a carbon paper on a drawing paper. This is how to estimate the position of carbon paper. Let's watch the video. Release the steel ball on the curved railing from 8 different heights h and record the value of r. This is how the experiment is done. Let's watch the video. Repeat again. Mark down the R1 on drawing paper. Repeat the step 3 times for each height. Make sure the R1 is measured perpendicular to the straight line drawn previously. Record the value of R1. Tabulate your data. Plot the graph of h against r squared. Measure the height h from the edge of the railing to landing surface. By referring to the graph h against t squared from the experiment A, obtain the value of t squared for h using extrapolation. Position your eyes perpendicularly to the marking on the meter rule and take the reading h. Make sure the meter rule is placed perpendicular to the surface of the floor. Calculate the value of g from the h against r squared graph. Determine the value of delta g. Lastly, compare the value of g obtained from both experiments with the standard value. Write your comments. Please watch the next upcoming video to guide you in lab report writing for experiment 2, free fall and projectile motion.